Hello everyone. Today we'll be discussing an experiment that we can use to test the validity of f equals ma, and in this experiment we'll be using vectors to investigate the effects of this equation. So, vectors are pretty important. Many problems involve a number of forces acting on a body simultaneously. So in this picture of a car we have thrust, drag, a reactive force from the weight, lots and lots of different forces, and most of them pointing in different directions. So we can figure out how they behave by modeling them with vectors. Vectors are of course a way that we can add forces pointing in different directions, not just in one direction and back. So by adding two force vectors together we can discover a resultant vector. That is, a vector that has the same effect of all the component vectors added together. Now vectors can be added together by joining them head to tail, as we've already learned. So if we take a red vector A and a blue vector B, we can add them together by joining the tail of B to the head of A to produce this green vector, A plus B. The resultant vector points from the tail of the first vector to the head of the last vector. In fact, using this technique we can add together more than two vectors. It has the same effect as all the other vectors acting individually. Now we can use weights and pulleys to investigate the addition of vectors. So we have a pair of pulleys over here. Pulleys. And three masses hanging off conveniently massless strings. So we have one force going down there due to weight, one force coming up, another force coming up, a force going down, and a force going down due to this weight. Now the apparatus can be adjusted until it is exactly at equilibrium, so that none of these forces are moving around anymore. None of these weights, rather. So when the middle mass is not accelerating, the sum of the forces on it is zero. So what are the forces acting on this? Well, there's the tension in this string, the tension in this string, and the tension in this string. So because this force is just transferred to this part of the string, we can sort of forget about the forces over here, and even the pulleys if we want to. The main feature are these three forces, and if the system is in equilibrium, then all these forces will balance each other. So the net force on the middle weight is zero. So this means that the weight of the middle mass is balanced exactly by the force exerted by the other two masses. And we can see that in this diagram here. The yellow arrow at the bottom is the weight of the mass in the middle. And we can see that the two forces generated by the other masses should match up exactly in order to balance the weight force of the middle mass. Those, of course, are the blue and green arrows. So the vector sum of each of these two forces should exactly balance out the weight force. We can see that if we were to add the blue arrows to the green arrow, we'd get an arrow looking something like this, which we can see is exactly the reverse of the yellow vector, and that's why they can cancel it out. So by summing all three forces together, we should be able to get a closed polygon, which is this triangle that we can see at the end of the animation. Alright, so now that we know our experimental setup and our theory, let's go and look at some experimental results generated by this apparatus. Analyze this data produced by the experiment. Start by drawing a vector diagram to scale, showing the sum of the 6 Newton and 9 Newton forces. So of course here we have three forces in play. One from the downward force of the middle weight, and two forces from the forces that go around the pulley from the other two weights. And we can measure the angle between the two strings being put around the pulleys. We find that is 59 degrees. Now we can use this angle, and the fact that this one is going straight down, in order to draw a diagram of the vectors here. So what we need to do is sum together the 6 Newton force over here and the 9 Newton force over here. And so we can do that by joining them head to tail. It looks something like this. So we can see that if we were to extend the 6 Newton vector out, then this angle here would be 59 degrees. And so when we're sketching it, we can find the value of this angle here simply by subtracting 59 degrees from 180. We get 121, of course. So when we're drawing the diagram, we have to make sure that all the angles match up completely. The vector should be drawn to scale. So if you're using 1 Newton is 1 centimeter, then this will be 6 centimeters long, and this will be 9 centimeters long. Now that we have this diagram, we can use it to analyze the resultant. So here we can use the diagram to find the magnitude of the resultant vector, which is of course the green vector in the triangle on the right. So by using a ruler, we're able to measure the length of this, and using our scale, which we use to convert centimeters into newtons, we can take this and find how many newtons it must be. And so, measuring our diagram, we find that the length of this corresponds to 13.2 newtons, which, as it happens, exactly matches up with our downward force of the middle weight here. So we can see that the calculated addition of the vectors matches up with the practical or experimental sum of the vectors. Let's look at some other data. Question 18. Analyze this data produced by the experiment. So here we have a 4 Newton force and a 7 Newton force from the two weights on the side, and a 9.5 Newton force going straight down from the weight in the middle. The distance between the angle between these two strings is simply 68 degrees. Part A. Draw a vector diagram to scale showing the sum of the 4 Newton and 7 Newton forces. So once again, we can use this angle here to calculate where we have to draw the 4 Newton force. And we end up with a diagram that looks something like this, with the 7 Newton force being in yellow, the 4 Newton force being in white. The question asks for the sum of the two forces, and that of course is the green force over here. Once again, we can use the diagram to find the magnitude of the resultant vector. So in this case, if we're using the same scale, 1 centimeter is 1 Newton, then we simply measure this in centimeters to convert it to newtons. In this case, if you've got all the angles right, you should get an answer that looks something like 9.5 newtons, which, as we can see, matches exactly this downward 9.5 Newton force. So that means that adding together these two forces produces a force that exactly cancels out this blue force, meaning that the middle weight doesn't move. One more piece of data. Question 19. Analyze this data produced by the experiment. Draw a vector diagram to scale showing the sum of the 4.5 Newton and 5.5 Newton forces. Now here we actually have a pretty big angle, 93 degrees. So that means that when we draw the two being added together, the inside angle will in fact be 87 degrees. So, drawing this, we end up with something like this. And of course we can see that now it's an acute triangle, because this is less than 90 degrees now. However, the green angle, we can still add the vectors together, and the green vector is the resultant vector from adding the 4.5 Newton force and the 5.5 Newton force. As long as we've drawn it to scale, we should be able to analyze the resultant vector. So we can use our diagram to find the magnitude of the resultant vector, and that ends up being about 7 newtons. If you've got the angles a little wrong, or the scale a bit wrong, then this might be a little off, but we can see that it still corresponds pretty much directly to our measurement of the weight of the middle mass over here. So we can see from this that our theory is matching up pretty well with the experiment. Our theory being the sum of the forces here, and the experimental result saying that these two forces are equivalent to this one. Now, obviously it's possible to analyze this triangle without doing complex measurements and stuff, simply by knowing the lengths of the triangle and knowing the angle here, which is of course 87 degrees. Of course, to do that, we need a little more advanced trigonometry than you're up to at the moment. So we'll just stick with analyzing the diagram. Alright, well, what about a conclusion for the experiment? Does the experimental result of adding forces together support the theory? If not, suggest a result for the difference between them. So in the real world, we can add forces together by pulling a weight with 3 different forces and seeing whether they cancel out or not. In theory, we can add forces together by using vectors. Of course, the analysis that we did in our previous question shows that adding vectors theoretically matches up pretty well with adding vectors experimentally. So we can say that the experimental result does support the theory. The force vector calculated by vector addition, that's our theory, matches the force vector observed experimentally. So, in this case, the theory was supported by the experiment. Alright, now that we're done with the experimental results, let's go on to some more questions to make sure you still understand how vectors work with forces. Question 21. On an aircraft carrier, the catapult wires used to launch an aircraft exert a huge force on the aircraft. So we can see from this beautiful diagram here that we've got 2 cables, 2 catapult wires pulling the craft forward, and each has a force of 20,000 newtons. Quite strong. We can also see from the diagram that both of them are at an angle at 30 degrees to the direction that the plane will move in. So our question then is, what is the acceleration of this 10-ton aircraft? Well, in order to find the acceleration, we'll need to know all the forces acting on it. So the forward force from each wire ends up being just a component of the force that's in this direction. For each force, there's a component in the other direction, but these cancel each other out, so we can ignore them. The only force we need to worry about then is the adjacent side of the right angle triangle. So that is 2 times 10 to the 5 times the cosine of 30. Because of course we know from our trigonometry that cosine of an angle equals adjacent on hypotenuse. And so the adjacent side, that is the one that we're interested in, this little vector going across here, is simply given by hypotenuse times cosine of 30, which is our angle. So that there is our formula for the adjacent side of the triangle, which is the force from each wire pulling it forward. So let's evaluate that. We can put this into our calculator to find an answer, and that is 1.73 times 10 to the 5 newtons. So that's the force that each wire is exerting forward on the plane. The sideways force they're exerted is cancelled out by the other wire, so we don't need to worry about it. So we know from our F equals ma that the acceleration is the total force over the mass. We know our mass, it's 10,000 kilograms. We know our force, it's this for each of the wires, so we can double it. And that gives us 2 wires times that force divided by the mass. Because these are just numbers, we can stick them into our calculator. We'll end up with 34.6 meters per second to the right, which is very fast indeed. Alright, part B. Find the time taken to accelerate the plane to 50 meters per second. To answer this question, we'll need the answer to our previous part of the question, which is, of course, the acceleration is 34.6 meters per second squared. Now, our equation to find acceleration is acceleration equals the change in velocity over time. So, the time is what we're looking for, and we know the acceleration, and we know the speed that we're getting up to. So we can rearrange this equation. Now it looks like the time equals the change in velocity over acceleration, which will give us an expression for time, which is exactly what we want. So we can substitute in our 50 meters per second for the change in velocity, assuming we start at rest, and 34.6 meters per second squared for our acceleration. We'll end up with this equation here. We can of course just put that into a calculator, and it will tell us that it takes 1.45 seconds to accelerate this plane from rest to 50 meters per second. Of course, 50 meters per second in kilometers per hour is a much higher number, something in the neighborhood of 140 kilometers per hour. So this is in fact quite a very fast speed especially if the plane gets accelerated to that speed in only 1.45 seconds. Question 22. A 2.5 kilogram metal ball is moving at 5 meters per second east. A force acts on it for 4 seconds, changing its velocity to 12 meters per second south. Now there are lots of numbers here, so it would probably be a good idea to write them down somewhere else and perhaps draw a diagram of the situation. So we'll start by looking at the scalars. Now remember, scalars don't have a direction, so we don't need to worry about the direction, only the numbers that we're writing down. So we start off with a scalar right at the start, 2.5 kilograms. So we'll write down the mass is 2.5 kilograms. The other scalar in this question is the time that it takes to change its velocity. So that'll be the time, 4 seconds. Now we have two vectors here, 5.0 meters per second east, so we can draw that over here, initial velocity, so that's VI, and of course 12 meters per second south will be our final velocity, so we can draw that over here. So now we've copied down all the values that we need to know, we can look at the actual question. Part A, find the change in velocity of the ball. Now remember, to find the change in velocity, we simply subtract the initial velocity from the final velocity. Makes sense, right? So our change in velocity, delta V, equals Vf, that's this red line, minus Vi, and that's this blue line. Remember that to subtract a vector, we have to start off by reversing its direction. After that, we can simply add the two vectors together. So once we've done that, our diagram looks something like this. We can see that we've reversed the initial velocity and added it to the final velocity, and we've ended up with this white vector here, Vf minus Vi. So this is our value for delta V. Because this is just a right angled triangle, we can use Pythagoras Theorem to find the length of the hypotenuse, and it turns out that if we have a squared plus b squared equals c, if we take the square root, if we substitute 5 and 12 for a and b, we end up with square root of 169, which happens to be exactly 13, which means that we don't have to worry about any decimal places for the hypotenuse. And of course, we need to make sure that we include the direction in the velocity, because it's not obviously east or west or anything like that. So we include a little arrow in our answer. Part B, find the acceleration of the ball. Now remember our equation for the acceleration. It's something like the change in velocity over time. We know that our time is 4 seconds, and the change in velocity is this vector here, this white vector. So our acceleration is 13 over 4, where 13 is the length of that vector and 4 is the time, which evaluates to 3.25, and it's in the same direction as the change in velocity. Alright, part C. Find the force on the ball. Now here's the interesting bit, because this is where we get to use Newton's second law, F equals ma. So we've got F equals ma, we can substitute our value for m, 2.5 kilograms. We can substitute our value for A, 3.25, in that direction, to that direction there. And that makes our equation look something like this, 2.5 times 3.25. And of course that evaluates to 8.125 newtons in the same direction. Now remember, normally it's the force that produces the acceleration, not the acceleration producing the force. So we would do this in the opposite direction. And this concludes the questions. So in this section we've learned about a way we can investigate the effect of vectors and forces, the difference between the theory of vectors and the experimental vector forces. So we've analysed that experiment, and we've also looked at a few questions that show us the effect of vectors on various physical situations.